Chapter 5, Example 4. The SAT reasoning test has 3 parts: writing, math, and critical reading, verbal. Each part has a distribution that is unimodal and roughly symmetric, and is designed to have an overall mean of about 500 and a standard deviation of 100 for all test takers. In any one year, the mean and standard deviation may differ from these target values by a small amount, but they are a good overall approximation. Suppose you earned a 600 on one part of your SAT. Where do you stand among all students who took that test? Since each test has a distribution that is unimodal and roughly symmetric, it is appropriate to use the normal model to discuss SAT scores. As I've mentioned earlier, you have to always check the condition, make sure that the normal model is appropriate, and state that before you conduct further work. So here, we're unimodal and symmetric. Those are the conditions necessary to have a normal model. Now we want to sketch this out. We start with the title, SAT scores. Then we're going to sketch in the curves. It's just kind of generic. Sometimes it's taller, sometimes it's shorter, but in general, this is what the curve looks like. Really, it just matters your scale. You could think of it as zoomed in or zoomed out. I generally use just the same shape and adjust the scale appropriately. We're going to put a number line on the bottom. 500 will go in the middle because that's my mean, and that number line is measuring points, so I want to put that label below it. Now, our standard deviation is 100, so one standard deviation is 100 points below 500 and 100 above. For the first standard deviation, we use the inflection point, which is where the curvature changes. So on the left-hand side, I'm curving up. We call that concave up. And then where it switches and starts going concave down, we call that the inflection point. That's where we put the first standard deviation. So I'm going to have 400 on the left and 600 on the right. So that's one standard deviation. Now I want to do 2 standard deviations and 3. When you sketch this out, sketch out a full normal curve, always do 3 standard deviations. So we'll have 300 and then 700. Finally, 3 standard deviations, which is highly unusual, 200 and 800. Now we're going to put in what's called the empirical rule. This is our 68, 95, 99, 7 rule. 68% of all SAT scores would be expected to be between 1 standard deviation. You don't necessarily need to do these dotted lines, but if you're showing the empirical rule, you need to show kind of a horizontal line from 1 standard deviation away, and that's 68%. Then 2 standard deviations, have some dotted lines so I can show you there. 2 standard deviations away, 95% of all of our scores would be between those values. And 3 standard deviations, we would expect 99.7% of all SAT scores to be between those values, between 200 and 800. That's the empirical rule. So I ask you to sketch out the empirical rule, or the 68, 95, 99, 7 rule. This is what your normal curve should look like. You should have a title on the top, a label for what the number line values are on the bottom, and then you want to put in 68% between first standard deviations, 95% between 2 standard deviations, and 99.7 between 3. And that tells you what percentage of all scores fall in there. Now, also it's important to note that this curve is symmetric. So, if I have 95% of all scores are between 300 and 700 points, 5% of scores are outside of that. Because we're symmetric, half of those scores would be below 300 and half would be above. So according to this model, we would expect 2.5% of scores to be above 700. Now your score was 600, which puts you exactly 1 standard deviation above the mean. 68% of scores are between 400 and 600 points, which means the remaining 32% is outside of that range. Since again we're symmetric, 16% of scores are below 400 and 16% are above 600. So you stand in the 84th percentile. 16% of scores would be above yours, but 84% would be below. A score of 600 would be 1 standard deviation above the mean. To verify that you're 1 standard deviation away from the mean, you can always use the Z-score formula. 600 minus 500 over 100 equals 1. But it should be pretty obvious to see that we're just counting by hundreds here, so you're 1 standard deviation above. A score of 600 would place me in the 84th percentile. About 84% of those that took the test would be expected to have a score that is lower than mine. What proportion of SAT scores fall between 450 and 600 points? So again, we have the normal model. We checked that in the previous portion, so we don't have to check the condition again. I have the model sketched out here. I don't have the empirical rule put in this time. I just have the number line and the basics curve in there. So what proportion of SAT scores fall between 450 and 600? I want to sketch that in. 450 is going to be between the 450, so I'll put a vertical line at 450, vertical line at 600, and I fill in the area between those because I want everything in that area. To figure this out, I need to find out what percentage of scores are below 450 and what percentage of scores are below 600. The way the normal curve works, when we look at a table, which I'll introduce in a moment, you can only look to the left side of the value. You can't look above. So we can find the area below values. First, I need to find a z-score for 450. 450 minus 500 divided by 100 is negative 0.5. Now I'm also going to find the portion below 600. So z equals 600 minus 500 over 100, which is 1. Now that we have the z-scores for those two boundaries that we have set, we have to find what percentage of the curve is below those. For one standard deviation, we can do that considering the empirical rule we just talked about in the previous problem, 84%. Now for negative 0.5, we don't have a rule that tells us that. We don't break it down for all these different groups. You don't want to have a 0.25, 0.75 that you just know. So we look at a table to identify this stuff. So I want to find the probability that z is less than negative 0.5. Again, we can't tell that just from the curve. And I want to find the probability that z is less than 1. When I know those two probabilities, the area between them, the difference of those would give us this area between 450 and 600. So we go to what's called a z-table. Table will look like this. It shows a normal curve above and it shows your z-score, and the probability that you're going to find from the table is the area to the left of your z-score. Always looking to the left. So I had a z-score of negative 0.5. If you look, this is the negative portion of the table. So I look on the left-hand side and I look for negative 0.5. I'm going to highlight that row. The probability I'm looking for is somewhere in this row. Now on the top, you have the hundreds places, the second decimal place, so 0.00, 0.01. Since I'm simply looking at negative 0.5, I want the first column, the 0.00 column. And we're looking for the cell where the row and columns intersect. And that's right there at 0.3085. So the probability that z is less than negative 0.5, 0.3085. The probability that z is less than 1. Now we already know using the empirical rule it should be 84. It's actually not exactly that, so let's look at the table and see a more exact value. Again, there's my z-table. And we're looking at a z-score of 1. So I highlight the row with 1.0, and then I want the zeros placed in the column. So that first column, and we get 0.8413. So it's a little bit more than 0.84. The probability that z is less than 1 is 0.8413. Okay, so we have that upper boundary and the lower boundary now. We want to find all the stuff below it. Remember, this is everything to the left. The probability that it's less than 600 is 0.8413. The probability that it's less than negative 0.5 is 0.3085. We don't care about the stuff to the left of negative 0.05. We only care about the stuff before it. So we're going to subtract. We're going to do the 0.8413 minus the 0.3085. So the probability that z is between negative 0.5 and 1 is 0.8413 minus 0.3085, which comes to be 0.5328. According to the normal model, 53.3% of all ACT scores would be expected to fall between 450 and 600 points. Since the question said proportion, it's okay to write it out as a percentage. If it said probability, you have to write it as a probability, which would be a number between 0 and 1. Also, we say according to the normal model, because that tells us we're using a model. We're not 100% sure that they're all going to be between there. We're not saying 53.3% of all scores will be between these values. We're saying this model indicates that we would expect to see that result. Remember, this is a model, it's not reality. Suppose a college says it admits only people with SAT verbal test scores among the top 10%. How high a test score does it take to be eligible? We've already checked the conditions on this, so we don't have to check it again. We'll start by sketching a picture of the curve so we can see what's going on. Sketch out the model just like we had before. Put the number line and everything. 16% of scores are above 600, and 2.5% of scores are above 700, so it's somewhere in the middle. You don't have to be perfect, just get roughly in the area. So I put a horizontal line roughly where I think 10% is. I shade to the right because I'm looking for the part above. Now it gets a little tricky here because remember, our table only tells us to the left. So the probability I'm going to look for the table is what's below that z-score that gives me 10%. So I'm actually looking to the left. If 10% is above, I'm looking at the 90% that's below. I want a 0.9000 in the table. Okay, so we're going to look at our table, and I want to look for as close as I can get to 0.900. And it looks like 0.8997 is the best we're going to get. I need to look at the margins in my table now to see what z-score that equates to. So I can put a box around that row and column. I'm in the 1.2 row and the 0.08 column. So my z-score would be 1.28. Great. 10% of scores means a z-score of 1.28. The question says, how high a score does it take to be eligible? It didn't ask about the z-score. Now that we have the z-score, we can plug it into that formula for finding z-scores and find the eligible score. Remember, the z-score formula says the z-score equals our data value minus the mean over the standard deviation. We know the mean, we know the standard deviation, we now know a z-score. So we can find that missing score that results in 10%. So z equals x minus 500 over 100. 1.28 equals x minus 500 over 100. Multiply the other side by 100, so we're just doing some algebra now. 128 equals x minus 500. Add the 500 to the other side. 628 equals x. According to the normal model, a score of 628 points would represent the top 10% of SAT verbal scores.